In this video, we're going to take a look at the books implementation of queues from the jsjf package. And there's two implementations. There's a linked implementation and an array implementation. We'll look at both of those. And they'll both implement the QueueADT interface. That's the book's queue interface. So it has methods for enqueue, which is to add something to the queue, dqueue, which is to remove something from the queue, first, which returns the element stored at the front of the queue, and then isEmpty, size, and toString methods. So as a reminder, a queue is a linear data structure where objects are added to the rear of the queue, over here on the left, and they're removed from the front of the queue. So there's two ways that we can implement this. The first is with links. The second is using an array, although the array implementation is a little more complicated than the array implementation of a stack, so we will take a look at that one second. So our linked queue implementation, we're going to have three members. We'll have an integer to keep track of how many elements are in the queue, and then we'll have LinearNode references to the front and rear node. Now, just like with a linked list, they're going to be single directional nodes, but having that rear node allows us to add things to the rear very easily. And since with a queue, we're going to add new items to the rear, take them off the front, having that second reference is very useful. So let's take a look at the code. As a reminder, the LinearNode class has a reference to the next linear node and the data stored at that node. Then it has a constructor that sets everything to null, or you can also pass an element, which again will set the next element to null. Then we have getters and setters for the next node and the element. So our linked queue class is going to have the three variables we said before, count, and then references to the head and tail. Our constructor will set up an empty queue, so the head and tail are both null, and the count will be 0. To enqueue, we're going to add something to the rear of the queue. The first thing we do is create a new node holding that element, and then if the list is empty, we set the head equal to that node, and then otherwise we set the old tails next to that new node. So now either the node is the only element in the list if it was empty before, or it's the last element in the list, it's the rear. And then either way, we set the tail equal to the new node because now that's the rear of the list. And then once we're done, we increment the count. Our dqueue method first checks to see if the collection is empty, and if it is, it throws an empty collection exception. And we define this empty collection exception in jsjf. It extends runtime exception, and all it does is call the super constructor, the runtime exception constructor, with a notice saying that the collection we're referring to is empty. So then, once we get past this, we know that the queue isn't empty. So we get the element that's stored at the head. That's the node we're going to remove. We set the head equal to the head's next element. So now that basically says, now we're not pointing to the head, we're pointing to the next item. And then we decrement the count by 1. Now, if this has the result of emptying out the queue would now be empty, and so the tail is null. Because in an empty queue, remember, the count is 0, and the head and the tail are both null. Now you say, when did we set the head to null? Well, if there's only one element in the queue, then that means that the head's next element is null. And so when we do this, that will set head to null. Once we've done all this, we return the result. That's the element stored at the head. The remaining methods are going to be left as an exercise for you. They should be pretty straightforward to implement. We can also implement a queue with an array. However, since the elements of the queue would actually move through the array, since we're removing from one end and adding to the other, as we add and remove, we'll need to shift elements to keep everything within the array. But an easier way to handle this is to use what's called a circular array. So here we have a circular array, and you see that it has 4 objects. The front is object 0, that's the one we'll remove next. And then the rear is 4, that's the next place that we can add a new element. Now notice this count is equal to 4, and that's this element, but the rear is what tells us where that actual location is. They just happen to be the same here. So as we add and remove things, eventually we can have a situation like this where now the front is 2 and the rear is 5, and there's 3 elements in the queue. And you'll notice these elements have sort of moved around. And eventually what will happen is as we add and remove more elements, we'll wrap around the end of the array back to the beginning. So here's a case where the front of the queue is now here. The rear is actually at 2 now, even though the front is at 3, because that's where we would add the next element. And we have 5 total elements in the queue. So now the question is, how do we actually implement something that looks like this? And this exact circular queue can be implemented with an array just like this. And you'll notice object 4 is at index 3, object 5 index 4, object 6 at 5, object 7 at index 0, and object 8 at index 1. And so if we go back, you can see here's object 8 at index 1, object 4 at index 3, and so forth. So they're the same queue. We're using a regular array that you should have seen many times before to represent this circular data structure. And by doing this, we don't ever have to do a shift. We just basically have these things move around and around. And just like within a regular queue, once it's full, we can resize the array. And as we do copies, then everything goes back to normal. So this is the actual data structure we're going to implement. Conceptually, it's that circle, but this is what it actually is going to look like. So let's see what that code looks like. So here's our circular array. Just like with the stack we implemented with an array, we have a default capacity, but that can be set in a constructor. And then we have front and rear. The front is where the first element is stored. The rear is where the next available slot is, and the count is how many elements are in the queue. So we initially start off with an empty queue. Front, rear, and queue count are all equal to 0, and then we create an array of our abstract type. Remember, we can't directly do that. We have to make an object array and cast it. And this gives us our brand new empty queue. If no parameter is passed in, we use the default capacity to make this initial queue. The next method we'll see is enqueue. And enqueue, if first off we check to see that the size is not the length. If it is the length, then that means we're full, and so we're going to need to expand the capacity. We'll see that method next. And then otherwise, we set the rear index of the array to that element. And then we do this. We don't just say rear is equal to rear plus 1. That's what you would normally see. But then we modulo it by the queue length. And what that does is if we go beyond the last index, by moduloing it by the length, that returns us back to 0 once we have a rear index that's equal to the length of the array. That's not a valid index, but if we modulo it by itself in that case, it'll go back to 0. So to expand the capacity, the first thing we're going to do is create an array that's twice as big as the one we had before. Then we're going to copy everything from the queue. And notice we're doing this arithmetic. We're going to actually start at index 0 for the new array, but we're going to start at the front of the queue. So we're actually, as we do this, we're going to shift everything over. And you may say, why are we doing that? That's slow. That's true, but we're already copying, and copying is a linear time operation anyway, so we might as well shift it as we copy. It doesn't actually add any real complexity to, time complexity, I should say, to the method. So our dequeue method does essentially the same thing that enqueue did, it's just from the other side. Here we get that result off the front. Now that reference is null because and it's available for use now. And then we modify the front variable, the front index, the same way we did the rear. We add 1 to it because remember, we're always moving to the right in that actual array. If we go back to our array, we're always adding things here. We're already removing things here. So the front and the rear are both always moving to the right until they circle back around. And then we decrement the count and return that result. And the remaining methods are left as exercises for you to complete.